In our next section, we're going to look at the configuration of route reflection, which we'll see is actually a very straightforward process. We'll also talk about how the BGP cluster ID specifically works and then how that's going to influence the advertisement of updates. But we'll see the big thing to understand about route reflection configuration is the actual underlying topology. So as the route reflector is going to process updates differently depending on what type of neighbor it comes from, the route reflector placement is generally going to be based on the physical topology. So for example, if we were to look at our particular network, and if we look at devices that are in central points of peering based on the actual topology details, for example, router 5 might be a good candidate for route reflection because it's an aggregation point for the DMVPN. It also has the connection to router 8 over here. Whereas if we were to take router 2 as a route reflector, it's not necessarily going to be the wrong decision. It just means that router 2 might not end up being in the data plane. So we're going to look at multiple examples here where we place the route reflector actually in the data plane and then we place it out of the data plane, and also look at the difference of how we configure this per address family, because when you're configuring the route reflector for IPv4 unicast, it doesn't necessarily imply that you're doing that for IPv6 unicast as well. Now, the configuration itself is going to be very straightforward. We just go into the process and we specify from the reflector's point of view who are the clients. So we say neighbor, whatever their address is, and then route reflector client. The key point to remember here, though, again, is that this is per AF. So the route reflector client statement does not go under the global BGP process. It goes under address family IPv4 unicast or address family VPNv4 unicast. Depending on which AFI, SAFI we're running, you can specify that the router either is or is not a reflector separately for those individually. Now, the client itself does not need to specify that the reflector is doing reflection. So it's not a negotiated attribute of the BGP process. We just need to configure it on one side. So first, let's look at this with configuring router 5 as the reflector, and we're going to configure it as the reflector for IPv4 unicast. Now, as I have the network pre-configured, right now we have three different ASs. We have AS9 on router 9, we have AS10 on router 10, and then we have AS100 in the middle. Now, previously AS100 was running a full mesh of peerings, and we're going to move this now to our route reflection. So specifically, the eBGP peering points are going to be between router 7 and router 9. This is eBGP. We're going to have eBGP between router 8 and 10. And then everyone under IPv4 unicast is simply going to peer with router 5. So let's look at the current state of the network, and I'm going to undo some of the BGP config here, and we're going to start on the external routers, which are router 7 and 9. So right now, let's look at the show run section BGP. And we're going to leave the eBGP configuration, but we're going to remove the iBGP config. So here, this is on router 7. Specifically, we're going to, actually, let's just do this. Let's say no router BGP 100. And we're going to rebuild this config, so router BGP 100. I'm going to leave the network advertisements on for the internal loopback space. And then we're going to say that we have a peering that is going to go just to router 5, where router 5 is going to be in remote AS 100. And it's going to have the update source of loopback 0. So we only have one internal peer, and then we have the one external peer. And let's leave the weight off of there as well. Okay, so this is on router 7. And then similarly on router 9. And actually, in the meantime, let me do this. Let's go to, or actually router 8, show run section BGP. So let me copy what it did have here. Okay, that's router 8. And then I'm actually just going to undo this on all of them. So let's say no router BGP 100. So here we have router 7's config. And then router 8, we're going to say, we're still advertising the prefixes. And now the neighbor is just going to be router 5. So 150.155. And then we have our external peer. So we can see configuration-wise, this is a much simpler design because simply we have less peers that we need to deal with. And then the reflector or the reflectors, plural, is going to take care of managing the rest of the peerings. Okay, so next time router 5, it's going to be our central reflector. So we're going to configure the process, router BGB 100, and then we're going to peer with all of the other neighbors. Now, you could do this individually with separate neighbor statements, or you could do it with peer templates or with peer groups. Really, it's up to you. In most cases, from practical deployments, it would generally use the peer templates or the peer groups, because if you want to add a client or change the policies, you just change the policy on the peer group, or you add the new neighbor to the peer group, and then they're going to inherit that. So really, personal preference. Within the scope of the exam, of course, it just depends on what the questions say. In this case, I am going to use the template because it's going to make it much simpler. So we're going to say that we have a neighbor that is called RR clients, and RR clients is a peer group. Okay, neighbor RR clients is going to have the neighbors in remote AS 100. It's going to be sourcing the peering from our loopback, so loopback 0 is the update source. And then the key change here is that they're going to be route reflector clients. Specifically, the peers are basically going to be all of the neighbors. It's going to be 1 through 8. So we're going to say that we have these neighbors, and they are in the peer group, which is RR clients. Now, the one that we don't need here is router 5 itself. Again, you could put that statement in. The CLI is just going to reject it. It's not really going to make a difference. Configure RR client. That should have been plural, clients. And it is case sensitive there. Now, on all of the other devices, they're going to have a very simple config. We're just going to say router BGB 100. The neighbor is 150.155, who is in AS 100. And neighbor 150.155, the update source is loopback 0. Okay, so this is on basically everyone else that is not router 5 inside of the AS. So this is router 1, router 2, 3, 4, 6, and then 7 and 8 already have this configured. Okay, our next step, once we configure all the neighbor statements, and we're assuming here that we had already tested transport beforehand. So here I'm using EHRP as the IGP to route between the neighbors, but again, assuming that if there is non-IGP reachability, then none of this is going to work, because we now have a multi-hop TCP session that's establishing between the neighbors, and IBGP doesn't have its own transport. So this means from router 5, we're assuming that we can already do this, that we can ping 151.1 sourced from our own loopback. Okay, if we now look at the show IP BGP summary, we should see that we have a peering to all of the other neighbors. Now again here, notice that we're not learning any updates yet from routers 1 through 6. They're not advertising anything into BGP. We are learning updates from the edge routers, though, from router 7 and router 8. So now the difference in this design should be when we learn the eBGP route on router 7, 7 is going to send this to 5. 5 should then reflect this back to the other neighbors. Now, if we think about how the physical topology looks here, and think about from router 3 and router 6's perspective, this is specifically the reason why the route reflector does not modify the attributes of the updates, because otherwise it would cause a loop in the data plane. So let's say, for example, that router 5 does collect the packets for these particular destinations, and then it's trying to use router 7 as the egress point. Now, specifically, the way that would happen is if we were changing the next hop value. So let's say that 7 advertises the update to 5, 5 advertises the update to 6 and sets the next hop to itself. This means that the traffic would go from 6 over to 5, 5 would then send it back to 6, and now we have a loop in the data plane. So this, again, is the typical reason that the route reflector is not in the path. Now, it could be, depending on the physical topology, like in this case, but in most realistic designs, it's just a control plane box that you have some sort of TCP reachability to. Then, based on how you're actually advertising the next hop value and then your IGP route to the next hop, that's how you actually leave the network. That's how the egress traffic is going to flow. So if we were to look at this now from router 6's point of view, and we look at the show IP BGP, one of the very key differences we should see versus the previous full mesh IBGP design is that we only learn about one path for every destination. And again, this is the disadvantage of using reflection, that the route reflector learns all of the updates from all of its clients and it makes its own best path selection. Based on which routes actually win the best path algorithm, those are the only ones that can be advertised. So in this particular case, what it means is that router 5 ultimately controls whether the traffic will egress via router 7 or via router 8. Now we can see this on the reflector itself. If we were to go to router 5, and if we looked at the show IP BGP, let's look at one of our best routes, for example. And again, let's look at the external route. So let's say show IP BGP regex, and then we're looking at just routes that have an autonomous system in the path. So again, this is basically saying any number 0 through 9, but there's one or more instance of it, so it's just any number here. So let's take a look at the route from router 9, for example. So this prefix is coming in from 9 to 7. From 9 to 7, 7 is advertising it to the reflector. So this is our IBGP peering, and this is our eBGP peering. The reflector is then choosing this as the best route, and it's advertising it on to everyone else. Now, technically, it also advertises it back on to router 7. There is no notion of split horizon in the case of BGP. So if we were to go to router 7 and look at this, which would be the debug IP BGP updates, and let's say just clear IP BGP star. And actually, I'll have to clear it on the other neighbor as well. Clear IP BGP star. And what we're looking for here specifically is this field. It says denied due to the originator is us. Now, as I mentioned, in the case of route reflection and in the case of loop prevention, the way that it's specifically doing this is with the introduction of 2 new attributes in the actual update. The route reflector gets a cluster ID, but the route reflector is also setting a originator ID. So in this case, router 7 is sending the route to 5, 5 is sending it right back. This is because router 5 happens to choose that as the best path. But when router 7 receives this back in, it says the originator is 151.77, which is basically my router ID, and it knows not to accept the update. Now, this could be another type of troubleshooting case like you would see maybe in external EIGRP or some of the other IGPs, that if 2 routers had the same router ID and then they were advertising their routes through a reflector, they wouldn't be able to accept each other's updates because they would have the same originator ID. So just like any of the other protocols, in a practical case, the very first thing you should do when you turn the BGP process on is to set the BGP router ID as a static value. So in this case, we're assuming it's choosing the loopbacks because we don't have any duplicate loopbacks, but there might be some legitimate cases where the loopbacks are duplicate, so that's why you want to set this statically. But here we can see that the updates are looping, but the point is that it is not an infinite loop. So they do eventually get discarded when we figure out either that we are the originator or if we're a route reflector and we see our own cluster ID in the list. Now what I want to show here specifically with clearing the table is kind of an interesting case that we can get into that, let's say from router 6's perspective, first off, let's see from 6, can we actually reach one of these external destinations? So let's say we ping 151.99 from our own loopback, and we ping 151.10.10 from our own loopback. Source loopback 0. Okay, then we're going to do a trace. Let's trace 151.99 from our loopback, and then also 151.10.10. So in this case, it's saying in order to get to router 9, we're going to go directly to AS9. In order to get to 10, we're going to go directly to AS10. But what I'm going to do in this case is to make a different change in order to make these external paths kind of look similar to each other. So what I'm going to do on router 9 is we're going to take our own update and prepend it out once. And then likewise on router 10, for its local route, it's going to prepend it out once. So they end up to have the same autonomous system path length. Because there's an interesting case that we can get into here with reflection that the convergence of the network, or basically which egress path that we choose, is going to be based on the order that the BGP process loads. And it has to do with the route reflector, the route reflector suppressing updates. And actually, there's probably a little bit easier way that I can do it, which would be let's say, let me think about this for 1 second. So from router 5's point of view, let's look at the BGP path to 151.99. And currently now, we are only receiving one route to this destination. Now, normally you would assume that the reflector should learn all paths in the network. But in reality, it depends on the order that it chose the route and whether it chose to continue to advertise other paths on. So specifically in this case, we're learning that the exit path is via router 9. What this means is that the route came in this direction, 7 sent it to 5, 5 reflected it down to everyone, including router 8. Now, at this point, router 8 learns the update in multiple ways. It's learning it on the peering between 9 and 10 this direction. So let's say that this is prefix A, and we're learning it via router 5 in this direction. We're learning it via B. Now, based on some attribute in the path, which in this case happens to be the AS path length, we say that A is not valid and B becomes our best path. But the end result of this is that router 8 stops advertising the alternate route. And this becomes now one of the disadvantages of route reflection. That if the network did need to reconverge, where let's say that the eBGP link between router 9 and 7 goes down, it means that 7 would need to send a withdraw message saying that the route is no longer valid. Router 5 would need to withdraw the update to 8. 8 would then need to invalidate the route, install the alternate path, and then advertise the update to the reflector and then back down. So in general, you would see that this is a very slow process to converge because depending on the number of updates that we have, it's going to be variable how long it takes to actually to process the updates. And if it's a full table, 500,000 routes, then it's definitely not going to be quick. But again, this problem is inherent to route reflection, that since the route reflector is now basically making the decision on behalf of the rest of the network, they only see the one possible exit point. But let's go ahead and make another change. Let's say we do this. Let's go to router 5, and let's say we have a route map that says local pref, and we'll say set local preference to 200. Which is higher than the default value. Again, we're going to come back to these attributes in much more detail later. But what I'm going to do now is to go under the process and say when we receive updates in from router 8, use the route map local preference inbound. Then we're going to clear IPBGP star. Okay, if we now look at the show IPBGP, and again, we're specifically looking at how are we routing to the external paths. Okay, right now it says that we're using router 10 in order to get to the rest of the network. So if router 6 does a trace, let's say to router 9, we trace 151.99, and we source this from our own local loopback, notice that we're following a different egress path. Basically because we influenced the route. We said in order to exit out, I want to prefer to use router 8 as the exit point, as opposed to using router 7. Now we'll see in general, local preference is one of the easiest attributes to use for this because it affects everybody in the AS. You can normally set it at any individual point and then it will inherently affect everyone. However, you can actually end up in some unpredictable results when you're introducing route reflection to a design like this. So let's say, like in this case, we have the route reflector centrally on router 5, and we should be learning two different updates. We should be learning the one that is via router 8 and via router 7. Okay, they're talking about the same prefixes, but they're different views of the topology because they're not both peering with the same ASs. We have 9 and 10, and then somehow on the back end, 9 and 10 are peering. So normally router 5 is going to choose one of these as the best path and advertise that the best path on, and typically we would see that the alternate egress point would then be lost. Now in this case, we're trying to influence which egress point we want by setting the local preference higher. We're saying we want to prefer router 8. However, there are certain cases here where if router 8 loads the process in a certain order, we would never be able to see it as an alternate exit. So for example, let's say that we go to interface gig 1.108 on router 8 and we shut that link down. This is the link that we have the eBGB peering to router 10 on. So it means if the link goes down, the peering gets withdrawn. Okay, this is what's called BGP fast external fallover, that if I'm connected to you on gig 1 with an eBGP peer and gig 1 goes down, I'm not going to wait 180 seconds to withdraw the prefixes. I'll just immediately flap the peer and then say we need to reconverge. So now as it stands, we should only have one egress point out of the network. Router 6 should say use 9 as the exit or use 7 as the exit specifically. Okay, next we have the case that the link comes back. The link comes back and the BGP update should be relearned. And if we now show IPBGP summary, we should see that we're going to regain the peer to router 10, which we do. And if we look at the show IPBGP, let's take a look at that specific destination that we were talking about before, which is the loopback of 9. Router 8 says I have two possible ways to get there. I have a way that goes via router 10, and I have a way that goes via router 9, but router 9 is indirect. This is coming from an internal peer, which is essentially the route reflector. Now also notice here, what is the best path? The best path is through the reflector, which means I cannot advertise it any alternate paths. So in this type of design, even though we're trying to influence the egress point by changing the local preference to higher, it doesn't actually work. And this is one of those cases that's technically considered to be a BGP wedgie, where a BGP wedgie means that based on the order that the process loads, you could end up in an unpredictable result, or what they call a non-deterministic result, that you said, I'm going to use local preference higher this way, so I should route out that way. But depending on who advertised the updates and who had to withdraw updates, you may never even learn that as an external path to begin with. So again, it really depends on what you're trying to accomplish with the design. If the main issue is scalability, but you don't necessarily care if you're choosing the best possible exit point, then route reflection is fine. But if we always want to say that I want to choose the closest exit, or I want to influence my individual exits, route reflection is not necessarily going to allow you to do this depending on where the reflector is physically in the topology. Now, you could also do other sorts of workarounds for this, like let's say we make router 6 a reflector, where router 6 prefers to route that direction, and we make router 5 a reflector that prefers to route in this direction. Then if we have clients that are peering with each of them, then they would be able to see the multiple exit points. But again, if we look at router 6 and show IP-BGP, this is the normal behavior that you generally do not learn about all exits when you're doing route reflection. When you're doing full mesh, generally you will, because typically the edge router is going to prefer its own external peering over someone else's internal route to some external destination. So what I mean by this is, let's say that we have some arbitrary prefix in the middle. We have destination X that 9 has reachability to and that 10 has reachability to. We then advertise this as an eBGP route to 7, and we advertise it as an eBGP route to 8. Now let's also assume that we're doing full mesh. So not only do 8 and 7 have direct peerings, so this is iBGP, everyone also has a peering to 7 and 8. Now, assuming everything else is equal, that we didn't modify the local preference, that the AS path ends up to be the same, 7 would say choose my external peer to get there, and 8 would say choose my external peer to get there, which means that they both advertise this to all of the internal peers. But in the case like we have now that we're using reflection, even though both of the entry points are getting advertised, one of them gets suppressed based on the selection of the route reflector. So it's something that when you're learning the protocol, it's inherently different than IGP, and sometimes they really don't make it clear enough that this is the desired behavior, that route reflection is used specifically to do this, to hide the topology information. Because then you can shrink the size of the control plane without having to say, I have 50,000 views in order to get to this destination. I'm just going to follow the decision that the reflector made, and then I'm going to use the next hop in order to get out however they want me to. Okay, there's a question, could I explain why did 8 choose 7 instead of 10 to get there in terms of path selection? So let's look at that specifically. And we are going to have to take a look at this in a lot more detail later, because when you go to actually modify the path selection, you're not going to be able to do that unless you can run line item by line item down the list and figure out why did it choose one path over the other. Now, specifically, the order is, and I'm going to list this just real quickly, and then we're going to come back to it later. Okay, the order is wait, local preference, local routes, AS path, origin, med, eBGP over iBGP. And then we start to get to, let's see, then we have the IGP metric to the next hop. Then we have our tiebreakers. Okay, tiebreakers are going to be things like who has the lower router ID, who has the oldest route. Normally you typically don't get down into this portion. You typically make the decision before you get there, normally based on your IGP metric towards the egress point. Now, in the case that you have multiple equal cost paths to the next hop, that's when you would be able to do multipath with eBGP, or technically multipath with iBGP, where you can say, I will use multiple exits in order to get there. So let's look, based on this particular list, we need to figure out why is it actually choosing one over the other. Now, also notice here that from router 8's point of view, actually, I looked at it from the wrong router. Show IP BGP 150, 199. Okay, so we are learning both routes, and it says here one of them is the best route. And then it's being installed into the table, and it's advertised to our update group. Okay, the update group here, again, this is what the dynamic value is. So you don't need to know really the details of this. It's just showing that it is being advertised to someone. If you want to see who does update group 6 actually mean, I believe you can just say show IP-BGP update groups, which we can. So group number 6 means member 10. So specifically, this means that we are choosing to route in, basically we have two choices. We have A and we have B. This was chosen as best, which means that we can advertise this onto router 10. But at the same time, it means we cannot advertise it to the person we are learning it from. In this case, we learned it from 5, so we can't advertise it to 5. Okay, that's how you would create a loop condition, that if I route through you and you route through me, then it's a data plane loop. To prevent this, BGP just says you can only advertise your best path. So if my best path is you, I just want to advertise it back to you. Okay, so let's go down the list then. Specifically for this prefix, first we're looking at the weight. Okay, the weight actually doesn't show up here because the weight is 0 by default. Okay, so the weight is 0. Then we go to the local preference. Okay, we have local preference of 100 versus 100, so neither of those win. Then we're going to the local routes. Okay, we're not the originator of this route. We are not the originator of this route. If it said from 0000 and at the bottom here it would say local, that means we are the originator. So for example, if we look at show IP BGP 151.8.8, that's my route. So I would prefer to route to me versus someone else's advertisement if it's a local route. But that's not our case here. So neither of these are local. Then the AS path. So an AS path length of 2 versus an AS path length of 1. This one is lower, so now this one becomes best. But again, the issue is now really based on the order of convergence, though. If I flap one of these peers and router 5 does advertise the alternate path on, that's going to change how the internal network is routing. So it's kind of like that case that they describe in the RFC, which is basically what is the implementation problem with reflection that specifically, and let me go back to the, or actually let me just show in the RFC where it actually is. If you search just BGP route reflector RFC, it's 4456. And then it is section 10 implementation considerations. Actually, no, section 11. It says one of the key components of route reflection is that we summarize the routes and we only reflect the best path. The end result of this is that in certain topologies, certain route reflector topologies, the route reflector may not yield the same route selection as that of a full IBGP mesh approach. So one way to fix this is that within your cluster, you could do a full mesh. So if we were to look at this network here and say, let's make this one cluster overall, we could have everyone peer with router 5, and then it would say that I'm the reflector. But then also everyone would directly peer with each other. This would mean that 7 and 8 learn their routes directly from each other. They don't learn it from the reflector. Then if we have another cluster, so another different geographic portion of the network, router 5 could reflect those on, and then it could use it in the data plane as opposed to the other routers. So it really depends on how big the network is and how the peering arrangements are laid out, whether this really comes into play or not. Now again, the other big thing to think about is the cluster ID. This is going to be the loop prevention when we have multiple reflectors. So let's say we make a minor modification of this and we're going to make another route reflector that is servicing the same exact clients. So we're going to make this as router 2. So if we look at router 5, who is the current reflector, and show run section BGP, we're basically going to take the same exact config and we're just going to put it on router 2, which is the only change I need to say is this. Okay, so 5 is a peer. Okay, for now I'm not going to do any modification to the attribute, so leave the local preference off. We're going to do that on router 2. And then on all of the other neighbors, if we show run section BGP, we're going to say that router 2 is also a peer. So 2.2. So this is on router 1, router 3, 4, 5, 6, 7, and 8. So next in router 2, let's look at the show IP BGP summary. And we should see that we start to form the peerings. Okay, we see we're receiving updates. We're receiving updates from router 5, who is the other reflector, and we're also receiving updates from we are receiving updates from the edge router. So the edge routers are 7 and 8. Now, as it stands now, 5 and 2 are not in the same cluster. And the reason why is that the cluster ID by default comes from the router ID, and the router ID is a unique value. It chooses whatever the highest loopback address is. So we can see this if we look at just the show IP BGP. It should say here what is, and actually I may need to say, how do we check this? Let's say show IP BGP neighbors. And it says that maybe it's show IP protocols. I'm looking for where it specifically shows my cluster ID. Show IP BGP cluster IDs. There we go. Okay, it says my global cluster ID is 151.2.2. Configured is nothing, but I'm getting this by default from my router ID. So let's look at this on router 2. If we were to look at the debug IP BGP updates, and then let's say we flap one of the external peers. So we go to router 8 and we drop the link to 10. That's going to cause it to withdraw the updates to 2 and 5. And then we'll add the link back so it can create the peering again. So on 8, we go to that interface, gig1, 108, and we shut it down. Okay, we should see the withdraw message come in on router 2. Okay, now the network is converged. We go back to router 8, we say no shutdown. Once they reform the peering, we should see that the updates are going to start to come in from from 8 and from 5. And we should also see that the update gets looped. And we may be actually stuck in the process now because it depended on the order. Let's say this. On router 5, let's show IP BGP. And it's saying use, let's see, use router 9 as the exit. I think that's the problem here. Let's say this. Clear IP BGP 150.177, which is this. So you can see here that the updates do get looped back to the reflector, but that's the normal case. So 2 is a client of 5, 5 is a client of 2, so they're receiving updates and passing them back and forth, but eventually they get filtered out. Okay, the only case that you would realistically want to do this is that if you have 3 or more clusters and you want to be able to indirectly route around a failure. So for example, let's say that the topology looks like this, where we have cluster 1, cluster 2, and cluster 3. Let's also assume that the paths in the network are physically diverse. So a failure of any of these one paths doesn't necessarily affect the other one. So they're not in a shared risk link group. Okay, we have cluster 1 that's made up of route reflector 1, and it's saying to do a peering with route reflector 2, and this is a non-client. So it's a regular iBGP peer, okay, in both directions. So we're doing the intercluster peerings, but they're not clients of each other. This means that when 2 sends an update to 1, 1 cannot forward the update on to 3. Because normal iBGP loop prevention says you learn the route from an iBGP neighbor, you cannot pass it to another iBGP neighbor. Now in this case, it should be fine. We don't necessarily need to pass the update on because we're assuming that 2 and 3 are already directly peering. But now let's say that that path physically goes down. This means that if the only way for them to route to each other is from 2 to send the update to 1 and 1 to pass the update on, if the route reflectors in different clusters are not clients of each other, they can't do this. So again, it depends on the overall physical design, because when you do make them clients, it does reflect the routes back and forth. And depending on the scale of the network, this could be an issue. If this is 20 million VPN-v4 routes, then yeah, that's going to be a problem to loop them back around. But again, from a practical implementation point of view, this is the default behavior. You don't even need to change anything. The route reflector will automatically filter out the update. Now, if we were to make them in the same cluster, so for example, if we went under BGP 100 and said my BGP cluster ID is 151.5.5, which is the same as router 5, we would now see that we're going to ignore these duplicate updates because we now have the same cluster list. It says here, reflected from the same cluster. So on router 2, if we were to now look at this and say, show IPBGP neighbor 151.5.5 advertised routes, we technically are advertising them to them, but when 5 gets them in, they're going to be denied. Because the cluster list is an inbound filter, it's not an outbound filter. So it's kind of interesting here how BGP works a little bit differently than IGP, where the updates do loop around the network, but it doesn't even matter because BGP itself is not used to route the traffic. We're still relying on the underlying recursion for router 5 to say, well, my route to the next hop is this direction. I don't care if 8 sent the update to 2 and 2 sent it back. That's not going to be the direction of my traffic flow. But as we see here, even with just these basic examples, the network does start to get pretty complicated. What's the end result of the traffic flow? So depending on how the route reflector chooses the best path, that's going to be the only one that it advertises on, and the clients then are going to have a limited view of the topology. So if you don't want that, if you want them to have the maximum view, that's when you go for iBGP full mesh. Now we'll see in our next examples, confederation is going to suffer from the same exact problem. Because based on where our view is in the topology, we're going to filter out the updates. Now, the other thing here I want to show real quickly before we move on is when you're doing this configuration per AF. Now, we will come back to this later, especially when we're talking about MPLS and also for IPv6. But just because you're a route reflector for one topology doesn't mean you're a route reflector for another one. So for example, let's say that we were to do this, where if we look at router 1, let's say show run section BGP, and we're going to make a change here. We're going to go to BGP 100, and we're going to say address family IPv6 unicast, neighbor 151.2.2 activate. And we're going to say under address family IPv6, which is actually where we already are. Let's say redistribute connected. And then show run section BGP. Okay, we're going to do this on all of the other neighbors. So we're going to say under BGP 100, router 2 is activated for IPv6, and then we're redistributing our connected routes. So this is on 1, 3, 4, 5, 6, 7, and 8. Okay, then on router 2, if we still debugging here. Show run section BGP. And what's actually interesting about this config, the only thing I need to do is to do this, to say address family IPv6 unicast, neighbor RR clients, activate. Because I already have the peering set up as the template, so it should allow me to. Now I still have to activate them individually. Peer groups are automatically activated when the parameters are configured. So I believe I need to say this neighbor activate. Yeah. So I need to activate them individually. So this is going to be under IPv6 unicast. Activate. And now the formats of our show commands are going to change. Let's say now instead of saying show IPBGP summary, we're going to say show BGP IPv6 or IPv4 unicast summary and show BGP IPv6 unicast summary and show BGP IPv6 unicast. Okay, we can see these are the actual routes. Now, as it stands now, I can't actually use the routes because I'm using IPv4 as the AF for transport. The issue I'm running into here is that there's no recursion to the next hop value. Now, we will talk about this in much more detail later when we look at IPv6 BGP routing. But the issue is that I'm advertising a v6 route but pointing it to a v4 next hop. This is not valid unless we're doing VPN v6 basically, which is called 6VPE. But we'll talk about that later. What I would need to do here is actually also to say, and I don't know if I can say this without making a major change. Let's try this. Route map X set IP next hop to loopback 0. Set IP next hop self. Then under BGP, address family IPv6, neighbor 151.2.2, route map X outbound. Set use own IPv6 hop not supported. No, I can't do that. I would have to manually set the next hop value. But basically, the whole point of this is that if we look at router 2 and show run section BGP, this config here and this config here, they're completely unrelated to each other. So you can be a reflector for one AF and not the other one. But the only problem we would run into in this specific example is that we're using the same peer group in order to activate the neighbors. So in this case, the peer group is dependent on the AF, where we're saying that everyone in Route Reflector clients is a Route Reflector client. Then whether we actually want to do this for the other AFs, we would have to do it here separately. So neighbor 151.1.1, Route Reflector client. Which would actually have to be that. But notice that they're independent of each other. It didn't automatically say, because you were an IPv4 reflector, that you would become an IPv6 reflector. So two separate commands here. Even though it's the same syntax, it's doing separate things. One is saying reflect v4 routes, one is saying reflect v6 routes. Okay, there's a question here, or with the same cluster ID, is there any point at all in even having the peering between the route reflectors? Because again, the issue was here that if the different clusters are not clients of each other, then they can't advertise iBGP learned routes. But the difference is they might have eBGP peers. So if these are your centralized points of presence, your route reflector might also be your edge router for centralizing peering. So in that case, yes, it does make sense to do a peering between clusters, because you're using that peering to advertise external routes as opposed to advertising your internal routes. But you're right, if it's only internal routes, then it doesn't make any sense because you're configuring a peering here that you would never use other than to bounce the control plane back and forth, and then it's just a waste of resources. So the real design depends on where the external peers are. But you can see just with this config that it's going to do this automatically, even if you don't set the cluster ID. So the cluster ID is typically only used when you have multiple reflectors that are servicing the same set of clients. If you have different reflectors with different clients, you would want different cluster IDs because otherwise they couldn't reflect the updates to each other. So keep this in mind as part of troubleshooting, but the easy way to figure this out is even if you don't look at the config, you can look at the debug, which is the debug IPBGP updates, and then it's going to tell you, or not show IPBGP, debug IPBGP update, and then it's going to tell you, was the update denied because of something like the, and we can't actually see it anymore here. Was it denied because I was the originator, or was it denied because I was already in the cluster list? It should tell you what the particular issue is. Just the problem is you have to parse through the updates. So what I would do personally is debug this to the buffer. And then you could parse on the buffer. You could say something like show log pipe include denied. And I think it usually shows it in caps there. And then it would tell you specifically what the issue was. So let's do this. Let's say logging console 6, logging buffered 7, logging buffered at some large value, debug IPBGP updates, and clear IPBGP in. Then show log pipe include denied. There we go. So these are the ones that are getting bounced back, but it's okay.